Hey, Karthik. This is Mike. I'm not hearing any sound on my end.
That you're focused on, and we have some measurements and observations.
Can people hear me? No. Okay. Sorry. Now whoever didn't hear anything, they didn't miss anything. So this is the first useful slide.
Yeah,
All
we
right.
hear you now.
All right. Thank you. Yeah. So the goal here is, can you encapsulate information into a model in terms of functions, operators, etc., and use them to make different predictions, right? So that's, I would call, if we achieve that, I would call that truly generalizable, because the systems that you want to work on a configuration are different. The other thing, compared to predictive system modeling, as I said, you're focused on a particular system, right? That's not what we're doing today. That's what we did last week. And yeah, much of this work is due to, actually, I got the wrong picture here. I'm missing Niloy, who is contributing to this very heavily. So Vishal recently graduated, and he's at NASA Ames, NASA Langley, and Eric is at Sandia National Labs. Chris is at Lawrence Livermore, and Cheng is a faculty at Kansas. All right. Okay, so some of the things that I talk about today will be in these papers. There's an annual review paper, and then there's a more recent review paper where I go through many of the things and add some perspectives. And then the meat itself, I would say the meat of what I'm going to talk about is in this paper from 3 years ago. And I'm going to show some very new results that we got pretty much last month. Okay, so what is the problem setup? So everyone here is probably working on turbulence in some form, but just for completeness, we have the Navier-Stokes equations. We can't solve them as they are for the problems we care about because of the disparity of scales. So we end up doing some kind of coarse graining, and coarse graining introduces the coarse-grained equations are not closed because you don't quite get rid of the full variable. So we end up constructing this. These equations are exact. This can be RANS or LES or any kind of coarse-grained model. So we end up introducing some kind of modeling assumptions to get a closed form of equations, where in addition to your coarse-grained variables that you began with, you typically introduce some secondary variables, right? These could be your, for instance, your turbulence, kinetic energy, and dissipation rate to close those equations. So really, the simplest way you can improve the models using data is by either introducing new parameters into your model or taking existing parameters in your assumed model forms and then calibrate them, right? And this is not new. In fact, from the beginning of time, from the beginning of modeling, people have been doing parameter calibration. So there is nothing very special to say about it, but it's certainly something that is useful in some contexts. Okay. So what we want to do here is potentially introduce, I want to call data as an operator, right? An operator could come in many forms. It could be an additional term in an equation, right? So maybe an additional term that changes the balance of production and dissipation, for instance. Or it could be an additional transport equation itself, right? That's why I call it an operator, right? So we want to introduce this, but we want to introduce it in such a way that not only do we get better match of quantities that we care about, but also do that in a very generalizable and consistent way, right? So that's the goal of what we're going to be doing. And I like to take questions, during the talk instead of waiting until the end, because I know nobody has a 50-minute attention span these days. So any quick questions on the setup before we proceed? All right, so far very straightforward. Okay. So one thing to keep in mind is it's not just fitting data to a curve, whether or not there is a PD involved, whether or not there is a machine learning process involved. One has to have a strong appreciation for the various levels of uncertainties that exist in these models and what exactly we're addressing, right? So here, this is from that annual review paper. We talk about 4 levels of uncertainties, right? The first one is just because you're introducing a coarse-graining operation, you're going to introduce uncertainty that is fundamentally irrecoverable, no matter what you do, right, with your model, right? For instance, even if you have larger dissimulations, anytime you introduce a coarse-graining operation, the coarse grain, there may be infinitely many realizations of the full field that may be consistent with the averaged or the coarse grain field. So here is an example from one of our papers where all of these ensembles have the same coarse grain initial conditions, but they all evolve differently, right? So this uncertainty is fundamentally irrecoverable once you've chosen the coarse graining operation. And then even after doing the coarse graining operation, we introduce additional assumptions like single point closures, right? Like the Cape silent model, for instance, or a bad example in that point, like you're not using 2-point, you're not using RDG, right? So these are all assumptions that come in. And then once you've even made the model choice, within that model, your eddy viscosity assumption or your pressure strain model, so those are introduced, and then in the last level we have uncertainties in the coefficients. So our model development process has to be cognizant of all of these and an inherent understanding of what is possible. Because if we just go ahead and try to fit any amount of data that we have, then you're going to suffer from generalizability. Okay, so that's a key thing to remember. Yeah.
I am surprised that you distinguish L3 and L4. Is there a reason that there is actually 2 different levels from?
Yeah.
Because essentially they're coupled, right?
They're coupled. L3 is you've chosen a model form. L4 is what constants do you use within that model form. Like C mu, you're ready. I know you're not a turbulence person, but if you've chosen the eddy viscosity modeler form, that would be L3. What coefficient do you use for the eddy viscosity is L4. But yes, I mean, it is. But here I'm really talking about constants in the model. But your argument is this could be a function of something, and then these two will be connected.
Because I can see very clearly, right, between L1 and L2 and L3, like there's a hierarchy of information.
No, but this is also clearly there is a hierarchy because this is choosing the functional form, and this is choosing constants within that functional form. This is saying y equal to ax plus b.
This is just
And this is choosing A and B. So it's very clear the distinction should be.
But both are just uncertainties in the model, right? It's not.
They're both uncertainties in the model, but whatever
But
you do
think
to
the
A and
function
B,
space and the coefficients are distinctly different.
no, here you're making a choice between ax plus b and
Right,
ax
you're
plus
choosing the
b
function
plus
space
cx
there.
squared. Yeah,
You're choosing the coefficients here.
that's really the distinction. Okay, so maybe I don't want to go too much into the philosophy here, but I'll skip this slide. There are some other peculiar challenges that turbulence has that also come in that we have to think about. All right, so first I want to start with this idea of feasibility. If we are, so this is just a feasibility of one part of the thing, right? Can machine learning be used in this entire setting, right? This is what we did all the way back, maybe 10 years ago. Even before we started on this path, we said, forget the fact that I have to improve a turbulence model, forget the fact that there's reality. So here we're just asking the simple question, can a machine learning model discover a known model? Okay, I'll tell you what the problem setup is. Can that learned model work within a PDE solver? Can this model generalize to things that it was not trained on? And can this extrapolate? Okay, so it's a much simpler problem setup than the questions seem. So we took a simple case. So we said, so for most of you who know turbulence, this modeling, this is one of the simplest models you can do. So this is the Spalart-Armaris turbulence model. It has transport. It has on the right hand side production, destruction, diffusion, cross production terms, and there are some complex relationships. So we said, so we're going to generate solutions, data snapshots by running this model in a CFD solver, generate data, and then start with a model that does not know anything about production, destruction, and cross production, and see if we can learn those terms using these machine learning algorithms, then plug them into the solver, converge the PDE solver on other configurations. Okay, so that's the idea. And then we looked at the model and we could identify some non-dimensional features in the model that the machine learning model would be functions of, would develop functions over. Okay, so that's the idea. So again, this is the setup. So we take some simple representative problems, run it, and then create features and outputs, right? Features are the three things that I showed earlier. Outputs are the terms that we hid from this unknown model, from this baseline model. And we are not really constructing the model. We want to embed that into this PDE solver and run it on unseen cases like train on 2D, test on 3D on a completely different case. Okay. Yeah.
Just trying to understand. So you would solve a flow using Spalart-Armaris model. So
Yeah.
you pick a flow to solve. Then you would compute these terms.
Yeah.
Right.
Yeah, exactly. Chi, omega,
Chi,
yeah.
omega, and you
Yeah.
would compute them. And then when you say I have the non-dimensional outputs,
Yeah.
oh, so you would compute all these terms from the
Actually, it's the sum of all of those. We would
Right.
raise, yeah, whatever is left, yeah.
From the solution you got, you would compute all these terms.
Yeah.
Take this group as input, that is output,
Output, yeah,
and feed that to your
neural network,
neural
for instance.
network,
Yeah.
and then see.
Yeah. Yeah.
what it gives.
Correct.
How did you come up with these terms? As in.
Oh, let's just be, so, the first thing is, yeah, it's a good question, relevant for later as well. We can't just use any feature because you want to be able to use features in a way that if I go to a completely different problem, it should make sense, right? So if I just use new hat as a feature, new hat maybe one in this flow and then billion in the other flow, so it wouldn't matter, but this makes sense. So we just we just did some local non-dimensionalization. It's a very important process, and even when we go to the real thing of improving models, the first thing you would do is, I'll actually walk through an example later on the real example. We want to look at physical features, use their intuition, use the physics, and use dimensional.
So this requires insight.
Exactly. That's where insight comes in. Yeah. And if you don't do this local non-dimensionalization, you can't divide by U infinity. U infinity doesn't mean anything. So it's a simple process, but it was very important. And it was not straightforward for us to do this. It didn't work the first few months either. So anyway, I'm skipping through this, but yes, we learned on very simple flat plates, 2D channels, airfoils, and we were able to predict 3D wing with a shot to a reasonably, it's not perfect. But even there,
What's the loss?
loss, you should probably read this paper, but we thought just using the loss of output minus input did not work. So we had to scale the features, and then we had to ultimately not just compute the loss outside of the CFD solver, but we needed to do it inside. Meaning, don't just take the output of the neural network on some data and then subtract it from the true data. Take the output of the neural network, push it into a solver, and then compare the difference between the two. So the solver is involved.
Okay.
And
And the learning is offline then, right?
The learning itself was offline. Yeah. But that's also not good when you want to improve models, right? So it was input X, and then remember, so a neural network is already like a highly nonlinear thing, and you're embedding that inside a PDE solver, which is also highly nonlinear, etc. So we needed to do a few things, but we proved that if there is an underlying model, it is possible to discover. It's proof of concept. This has not solved anyone's problems just yet. We did a much more complex problem with transition. And in all of those cases, with a little bit of intuition, we could do it. But again, this is of no value on its own to anybody, but it's a go, no go type of check. Quick.
Just to confirm, right? What you showed was that your discovered model is at least in the domain that you were training it on, it is able to learn the original, right?
Correct. Correct. Yeah. And also this question of, because we've scaled the features correctly, this generalization is addressed, right? So yeah, go, no go. So yes, it's not a silly idea. We can do this. All right. So now let's go to improving models. So can we do this to improve models? And typically a good place to start is by saying, okay, this is the anisotropy tensor, which is taking the Reynolds stress, dividing it by the turbulent kinetic energy, and then subtracting, the diagonal term, so to speak. So that's the non-dimensional thing. So let's say your RANS model predicts this anisotropy. Can you basically augment the Reynolds stress with some new model forms, right? So this is the classic tensor basis expansion. If you assume that your stress-strain relationship is a function of strain and vorticity, then you get a particular expansion that you can rely on, assuming that assumption is correct, which is not, but So then you introduce some machine learned functions that choose, what weight to put on each of the tensors, right? So that's one way of doing this. So the same approach that I mentioned earlier, if you apply it to improving models, this is how it would look like. You would go run a DNS, you would collect your features, as I showed in the previous slide, you would collect your whatever your functions that you're introducing into your model, and then you would do some kind of a learning, and then you would shove that learning into that model, like I showed you in the previous slide, previous example, and then you get your improved model, and then you would go predict. So, and this is probably what is the proposal we wrote 10 years ago, that this is how we're going to do turbulence modeling. So for some reason they funded it, but it didn't work in many cases, and the community itself was probably until 2020, most people were doing these things. This kind of approach was okay in that previous case where we did not have to worry about consistency, okay? Whereas in the real problem, this won't work because of an inconsistency between what you learn and where you predict. So let me explain. So let's say you learn from DNS, right? The DNS has perfect information. Your K, your epsilon, your omega, no, omega is fake, but whatever. Your K, your epsilon, all of the other secondary quantities that you compute in your DNS are pretty much close to the truth. Whereas in your RANs, your K and epsilon, these are there to provide you scales, length scales and time scales and things like that. And by definition, they may not be precise. They're just variables there that are there to help you achieve your actual goal. So if you go learn your relationship in the DNS data and then try to put it into your RANS model, you create that inconsistency between the perfect world of DNS and the imperfect world of RANS, right? So the model doesn't know what to do because, like I said, the features themselves in the DNS are perfect, but in the RANs, they're not. So your goal is to predict the Reynolds stresses correctly. Your goal is not to get every minute detail of the flow field. And unfortunately, the features that our model ends up depending on, are some of these finer features. So, so this a priori learning effort does not work unless magically your features are correct in the RANs. Okay, so this fundamental inconsistency, at least we spotted it by 2014, and we started, fixing that. Right, so this is some inconsistent approach, but it's the easiest approach of going and grabbing, data from DNS and putting it into RANs. Any clarifications needed here? Yeah.
So when you do the model of augmentation,
Yeah.
you trying to add new features you want to add to the model,
Yeah. So what do you mean by new features?
like, for example, you know, like your model will be in the form of you have linear parts, weights, and then the bias, and then
Yeah.
When you learn that, and you find it might not be that, so you're going to add introduce another parameters to the model.
No. So yeah, I mean, yeah, it's more or less, right? So this is a linear part, and then this is the part that you're learning, right? But my point is, what you learn is a function of some features. And those features may look very different in the DNS environment and the RANS environment, because the RANS, so the compact way of saying what I just said is you have to learn to make improved predictions working with corrupted data, right? The RANS corrupts it. Yeah, so that's the point, yeah.
Interpret as this is a conflict introduced in the L2 uncertainty.
It's not just L2, it is the fact that, as I said, yeah, it's all of them. It is all of them. It is all of them because of the fact that you made all of those assumptions, when you're actually solving a problem, the features that you get would be different from the true value of the feature, because DNS has L1, L2, L3, L4 all accounted for. Yeah, it's those irrecoverable things. All right, so how do we fix it? So again, look at the previous, yeah.
Since that equations are different, so in some sense, they're just two, although we like to think of the variables as being the same, they're two different systems, dynamical systems.
Yeah.
Nance equations and the.
Yeah.
But we're trying to make a connection of the variables because of our hope in terms of what we.
Yeah, it goes back here, right? So we basically introduce, yeah, forget this. So we are approximating this by this. And our goal is to get U bar correctly. But to get U bar correctly, we need V bar. And the V bar will never be correct because they're just made up quantities. And in some cases, like K omega model, it's completely made up. There's no connection. Yeah, that's the idea. All right, so how do we fix this? So the a priori doesn't work. So we developed a series of approaches, back in 2014, to introduce model consistency. So what do we do there? So the model itself is included in the learning process. Okay, so how do we do that? So think about, instead of taking DNS data and learning the functions and features from the DNS data, what we do is we start with the RANS model, and then we add some, say, correction to that RANS model. The RANS solution improves, and then we keep improving it. And then your RANS model reaches a certain level of accuracy. And then we learn the features and the functions from the RANS model itself, rather than learning from the DNS. So earlier, this was the RANS model, this was the DNS model. You grabbed stuff from the DNS model and then you shoved it into RANS, okay? But here, again, this is the DNS, this is the starting RANS. You solve an inverse problem to improve the RANS, and then you forget the DNS, and then you learn from the RANS approach itself. So now you're consistent with the underlying model, okay? So that's why in the previous approach, there was no model in the training. So now the model is involved in the training. I'll show you more precisely how this works. So I should have made this a little simpler, but fine. So now you have data, okay? So this can be DNS data, or it could be pressure measurements in an experiment, okay? So I call that Y data. This is what you measure, or this is what you know as you trust. And then you introduce some functions into the RANS model, and then you make a prediction from the RANS model. So now you're comparing the difference between the data and the model prediction, and you're trying to minimize, some regularized version of that, right? So earlier you were trying to minimize the difference between the data and your neural network model, but here you're minimizing the difference between the data and the output of your improved model, right? So this minimization is subject to the constraints that your PDE is satisfied. Okay, so that's the model consistency step. So yes, it addresses model consistency. You can use these locally geometrically invariant quantities as features. And for every new data set, you solve a different inverse problem. So it's kind of scalable in that sense. And again, for many experimentalists in the audience, this is really good because now you don't need fields of data, right? Earlier, you were taking a full field of DNS data and then trying to build a model. But here you can work with very sparse data because you're going to be learning from the RANS model rather than from the DNS itself, okay? And that—
training is not gradient based.
Training is completely gradient based. We use adjoints. Otherwise, you can't do it. Because this is a very high dimensional inverse problem.
But you could otherwise write everything in a differentiable solver. That's the other.
Sure, yeah, you could do that. And the differential solver will use some—
Which we will just do the adjoint.
Exactly. You can't avoid the adjoint in this high dimensional problems.
And was there, did you try a non-gradient based? Like
Yeah, we've tried some ensemble methods. They work okay when They work okay, but not quite. So here is a simple example of just the first step, the inference process. So here is a well-used NASA test case. It's just flow over a bump. The original model, this is pressure. The original model predicts the green line. The data is the blue. And then you solve an inverse problem to correct the ratio of production dissipation in the SA model. And then you're improving the skin friction. You're improving the CV predictions, right? But in all of these cases, you'll be very careful of not overfitting to the data. This is one simple way of diagnosing it, right? So here is the Reynolds stress, the true Reynolds stress, the Reynolds stress in the baseline model, which is UV prime, U prime, V prime, and then the Reynolds stress from the improved model, right? So even though you are just using pressure data, right, on the surface, you seem to be getting a much better Reynolds stress prediction over the entire field. So that's, this doesn't prove anything, but it's just one level of check. So this is, so you're not just fitting there and not getting everything else. So this is more or less doing things for the right reasons. I'm going incredibly slowly. I'm still in year 2015 now. We have nine more years to cover.
Those are the important years anyway.
Yep, that's right. Got me tenure or something. All right. So, okay. So that was. Hopefully not, but anyway.
At least not for now.
All right. Okay. So, so that was the first step. So what did we do there? We introduced functions into the model, and then we inverted the entire field to get the value of the function at all of those points, okay? All of the grid points. So this is not a generalizable model because this only explains how to improve this particular flow. It has no predictive capabilities. So the idea is to solve many inverse problems that are representative of the physics that you're trying to fix, and then apply a learning algorithm, right? And then generalize it. And this kind of approach we use called field inversion in machine learning. And lots of people have pursued this with varying degrees of success, some very successful, some not. So anyway, this is what we're doing earlier. And again, this was one of those earlier examples. Yeah, this is 2017, at least when it was published. So, and this was implemented in a commercially available CFD solver called ActiSolve. It's Altair solver. So here is one of the early examples we did. So we took data from this red airfoil at a few angles of attack and a few Reynolds numbers. And we wanted to predict on these green and blue airfoils at different angles of attack and different Reynolds numbers. Okay, so that's, and we start with the baseline SA model. And again, there's just more detail in this paper, but this is, one of our early successes where we showed we could do this, we could be generalizable. And, some of the amazing results we got early on, which I'm not showing here in the same example is, we were initially starting with using a few pressure measurements at a few Reynolds numbers, okay? And then that was improving the model. And then my student said, okay, I don't want to use pressure, I just want to use lift. He was just using lift measurements. So basically this entire field is inverted based on one data point, right? So that's like information content is very high. Just using lift measurements at for a few points, we're able to improve the model and show it improves predictions in unseen cases for different angles of attack, the entire person distribution, velocity, etc. That doesn't mean we've solved this problem. It just shows that yeah, it is possible, and we can get some degree of generalization, even though these are all airfoils. The fact that we were able to use very sparse data and get better predictions was pretty, we're pretty happy with the early work. And there was even a case where we went to the extreme where we used training data at one location, right? And then, solved, but there were maybe different errors numbers. And we were able to improve prediction. So the high level idea here is you have a model, and then you have some kind of machine learning augmentation based on some data. But because you're still constrained by the physics, you can make predictions. And what makes us predict is this idea, right? So clearly, any engineer or scientist for that matter would say that this is extrapolation, right? So I trained this on this airfoil, and then I'm predicting on these two airfoils. So in some sense, in some realistic sense, this is extrapolation. But in the machine learning sense, what is happening here is, I thought I had that somewhere. What? I don't know, I lost that. Okay, maybe I'll revisit that point later. Anyway, so, but yeah, early successes, but then there are still many open questions at the time, and some we've answered, some we've not, right? How do you extract relevant information from data, right? Not just every data point is not the same. How do you learn model augmentation from data that are realizable? How to enforce constraints? So far, I've not talked about constraints other than the fact that it is constrained by the PD itself. In some cases, you want Reynolds stress to be realizable. You want, certain bounds to be satisfied. We kind of addressed this consistency between data and model augmentation, but we did not quite nail it. Because even though in the inference step, you're fully consistent, in the learning step, you're still not dealing with the outputs of the PDE. There are a few other things. Okay, so the next step in the evolution of these models, this was circa, I would say we started this work about 2018-ish, 2017 maybe. So we said, okay, so now instead of separating the inference and learning steps, let's combine them in the same approach. So we said, okay, now I'm going to embed a neural network into the PDE or any kind of learning model. And I'm going to directly infer the parameters of the neural network, okay, as a big inverse problem, right? So again, here is the data, the real world data. Here is the output of the PDE with the embedded neural network. And I'm going to basically optimize the parameters of the neural network such that this loss function is minimized. So now the inference and learning are strongly coupled, are there in the same step. So here you have complete model consistency compared to the previous approach. And anything you infer is learnable by construction, okay? Because earlier you could learn these you could infer very complex functions, but then there is no guarantee that the neural network will learn all of those in a generalizable form. Whereas here you're solving, this K is number of data sets, right? So you're taking, say, a dozen data sets or 20 data sets, whatever it is. You're solving a large inverse problem that develops a model augmentation that improves over that entire ensemble. And you can also adjust which data you trust more. And then there's a Bayesian formulation, which I'm not going into. Okay, so that's how we got to this slide. Yeah, so the key thing here is, yeah, even though in the physical space, it seems like you're doing some extrapolation. Like in that first example I showed, you were learning from airfoils and flat plates, and then you were predicting in 3D geometries. So in the physical space, that's all extrapolation. But in feature space, which is what really matters, you're still interpolating, right? So the idea is your physics-based model plus your PD constrained optimization or your model consistency plus a well-constructed feature space can give you extrapolation. So that's the key thing, okay? So in our long journey, at least, we are addressing these little pieces. All right, so how much time? Okay, we are in 2020 now, or 2019, I don't know. So, and then of course, now that we, got proof of life, then we started becoming more careful. We're like, okay, now we are asking the questions that real modeling people would ask, right? Where to augment, how will it affect it, how to design feature space. And this is what I'm going to focus the rest of the presentation on. What function class to use. And then we want to be, much more careful because I said, if you use a Q as a feature, maybe this is how your function will look like. Use QQ, your function may look different. So you got to pay attention to how you construct the feature space, right? Not just enforce model consistency. And typically, this is what happens in many of the engineering applications. So this is feature space. You may have a lot of data in some part of the feature space. Maybe this is your boundary layer, for instance. And you have very little elsewhere. And if you shove a complex neural network into this, it won't work, okay? So I think the general philosophy is captured here. So again, go back to the very first slide I showed. This is your training data, okay? So this is your canonical shock boundary shock turbulence interaction that may give you, so this is physical space and this is feature space. Okay? It may give you, populate that region of feature space. Some other data set will populate this region of feature space. And if you want your model to be generalizable, you want to have data or you want to have feature transformations that lead to a well-populated feature space so that even when you go to a problem that you've never seen before, hopefully it falls in the right part of feature space. And much of the work that we did, that we've been doing of late is engineering that feature space to ensure you get some kind of generalization guaranteed. So
give a real example of that dimensionality reduction too.
Actually, yes. I have a choice to make, but anyway, I'll certainly show you that one slide that I have on it. So again, now we're getting into serious modeling, right? This is not just, hey, here is my learning model, here is my adjoint, So now we want to go through this process much more carefully. And Mahesh, I think I may have told you this when you were interviewing here, right? So I want to engage in some kind of long-term development where we have high fidelity simulations and we have experiments and we actually treat this as this whole thing and we just look at the entire box. So officially, this is our 4th day in the center. So I think it's a good start. So, and we have a bunch of years left to achieve this. So I'll show you very quickly. I won't have time to go through all of this because I have a sharp stop. But here we're doing bypass transition modeling. And I will not explain what it is, so you can look it up. Details are not important. We introduce model augmentations in a certain way with a certain logic. And here I'll show you a very simple way of thinking about the feature space, okay? So let's say you're improving any model, forget that this is transition. And you're working with an eddy viscosity model for whatever reason. So you know that the eddy viscosity and the laminar viscosity are important features, right? So that's probably the very first place you would start with if you're doing linear viscosity models. Now, how do you convert that to a feature? The simplest way would be nu t over nu, right? Or you could do these other things. But my student came up with this. And if you're a statistician or a machine learning person, this is what you would do. But this is completely useless in our physics case because max and min don't mean anything. Only meaningful non-dimensionalizations mean something. So we could use this as a feature, but this is not a safeguard because in some cases, you may go from 0 to 20. In some cases, you may go from 0 to 200, right? Because this ratio can be very high in some problems, very low in some problems. So my student came up with this way of non-dimensionalizing. And this really works, at least in some sense. Not so much in other senses, which we recently learned. But this is just to give you the philosophy of being careful in constructing the feature space. If you use this feature and your flow is laminar, eta is going to be 1, okay? And if your flow is highly turbulent, eta will be closer to 0. So whatever your data is, all of your data will fall between 0 and 1 in feature space, right? So you're effectively bounding the feature space by construction. So very simple idea, right? But these ideas are taken forward. And of course, then you use your knowledge of flow physics to figure out what your non-dimensionalizations and bounds should be. I'm going to skip all of that. And then instead of just throwing a neural network at the whole problem, you can be much more deliberate about how you construct the feature space, because all of your model improvements live here. Okay, so this is the most important thing. So one of the things, since we all come from CFD, we said, okay, I don't want to leave it to the neural network to do its business in feature space. I'm going to just mesh it up. I'm going to discretize feature space using some regular mesh. And then I'm going to use localized learning within each of those elements in feature space so that I have much more control over it. Because I may have 1 million points here and 1 point here. So I want to have control over it. It has its own things. And of course, putting together the big framework is, I mean, in a real solver was hard, but it's doable with good students. And maybe I'll very quickly run through 2 examples. Sorry, I'm speeding through. But again, I'm here in the center and we have a lot of other discussions to have. So what I'm going to show is almost the ideal that I started with. I'm going to learn from just 2 flat plate cases, and I'm going to predict in other flat plate cases and turbine airfoils. Okay. And long story short, we can do it. And so to your question, if I had more time, so this is a 3-dimensional feature space. And I'm showing slices of the 3D, right? So this is dimension 1, dimension 2, dimension 3, and then I'm showing slices of dimension 1. Because we have full control over feature space, we can actually probe it. And more or less everywhere it's 1, which is the baseline model. And then in some parts of feature space, you have some activity. And each of those activities, we could relate to like certain physical things. And now I have this feature space and it kind of works well. Yeah, this is the model predicting in these unknown, unseen compressor airfoil cases. And it doesn't obviously predict every case better, every case really well. In some cases, the prediction improvement is good, but not quite there. But this is because the adverse pressure gradient in this case is much higher than what we saw in the data. In fact, the data was actually did not even have adverse pressure gradients. So with more data, it can be improved. Last example I want to show, this is more recent work. We are in 2024 now. We have some hypersonic problems where we're looking at model improvement in the Reynolds stresses as well as the turbulent Prandtl number, which in most models is considered constant of 0.9, right, based on thin attached boundary layers. But we made that a function of some features. And again, based on some fairly simple data sets, we were able to make predictions on more complex data sets, including some flight geometry type cases. And even though we are not perfect, at least we are able to show that you can learn from these simple problems and then quite distinctively improve predictions in these complex problems. Again, doesn't mean this problem is solved or we have nothing left to do, but slowly these techniques are maturing by using better judgment and better use of tools that we have. So Yeah, so finally, like I said, some of the most important points is, I mean, how you select features is probably the most important piece of the whole thing. If you have model consistency, they have to have some kind of local non-dimensionalization. They have to be kind of bounded, but just because they want to be bounded, you don't want to make it a very hard function to learn. And then you can apply constraints. And again, a little more philosophy here. Just because something makes sense from a physics perspective, we don't need to shove it into the model, right? Just because some invariant sounds appealing doesn't mean it is going to help. We just need the right physics and the appropriate constraints that is needed for the prediction goal. Okay, so I'm saying this because there's a lot of appeal in thinking of some invariant and saying, oh, my model satisfies that invariant, but it may not matter to the predictive goal, or it might even constrain the model unnecessarily. So again, you can, I skip through a lot of detail, but I would say, yeah, some of these papers contain that level of detail. And my very last slide here is, if you want to move towards a more complete model development process, what I spoke about today is something about function representation, right? Something about constraints, something about model consistency. Like this is all I talked about today. There's a lot more work in unsupervised learning. How do you design experiments and simulations that don't just give you interesting physics, but give you the right amount of information to help improve the gaps that you're trying to address. And I didn't talk much about UQ. We've done some of that in this context. And yeah, some more, formal things. So, yep, that's pretty much my last slide. And we kind of made it. I have 4 minutes before I have to leave, but we can always chat more later in the semester. So thank you very much.
Thanks, Dr. Questions?
Yeah, go ahead.
So all the work you augmented those models using your previous known models and experimental data.
Yeah.
But I had a case, and I want your opinion on it, where I had experimental measurements for tracking parsimony.
Yeah.
3D to 2D measurements with surface of the wing, and experimental data on the surface of the wing suffers from high uncertainties and does not conform out to the known approximate condition.
Yeah.
Can I use this approach in the reverse way to supplement experimental measurements and make it conform to the physics?
Oh, yeah. I mean, yeah. So, yeah, you can certainly do that. But even if your data is noisy, but you have some sense of the noise or some sense of the error, that can even be encoded into this process. You can deal with ugly data by using that as a covariance in the loss function. But to answer your question, yes, we've used in some other work, we have sparse measurements, and then we have the physical model. We use that to basically extract much more information out of the measurements, assuming the underlying equations are true. But there can be a synergy, right? One can inform the other. You could have trustworthy data somewhere in your field that can be used to hopefully improve the model. And then you can use them. Yeah. 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 So maybe your PIV is very good here, but kind of very bad there. Of course, there's no magic. This has to contain information that's relevant, right? Just because it's accurate here doesn't guarantee better predictions. But yeah, I mean, mathematically, it's doable. Yeah, physically, that there are some connections. Yeah. Sahil, I'll answer your question in the group meeting at 2 p.m. Yeah. Yeah.
So you showed the full or final or current feature space for the hypersonic case.
Yeah.
And my question was, are the first three, most of those I felt like were efflux related, but are the first three the same 80123 that we were looking at for the
more or less, yeah. Yeah, this was before that. Yes, these are almost, this is the non-dimensionalized strain, and what is, this is S K or epsilon, is omega K or epsilon. Yeah. Yeah. Right.
So, I have a question about the model consistency. So if you want to do, the train that reduce all the model, but you want to guarantee the model consistency, can you do that by using this, inference operation, or you need to do something like, if you want to do that, better model on the vehicle, but then you can interpolate and make that guarantee the model consistency. Yeah,
I mean, model consistency goes beyond outputs. It talks about the inputs, and usually you have less control over the inputs. But you can also have, you can have a learning problem where your loss function contains the features also. It makes it a little harder, but yeah, it's technically it's feasible. Yeah. Yeah. Yeah.
Very naive question, I haven't done fluid mechanics in years and years and years, right? Enough exams, not have to look at it yet.
Yeah.
So let's say I have a structure and I suspect it's going to do something interesting in terms of fluid surface interaction. And I can do measurements at laminar regime, or maybe like low velocity turbulent regime.
Yeah.
And then I want to predict, what's going to happen in the hypersonic regime. How do I go about doing that? Like, will your approach allow for training, let's say, to happen in the easily measurable regime, and then be able to make predictions in the hypersonic regime?
Yes. I mean, technically speaking, it's possible. We call it hierarchical augmentation, right? Even if you're going to go predict in some complex regime, you build your model on some foundations, right? You maybe still believe in the law of the wall. You believe in certain things, right? So I don't have it here. I mean, I have it as the bullet, but I don't have the slide. So we call it hierarchical augmentation, where when you introduce corrections to a model, fortunately, I don't have it here. You introduce it in such a way that physics-specific corrections can be introduced on top of each other. Okay, so here in this particular case, we were accounting for, this is not as drastic as the physics that you mentioned, but there were very strong adverse pressure gradients that were not in the data set. But we had a lot of data for the non-adverse pressure gradient cases. So we trained the model, and then we left the model structure in such a way that when you do get these adverse pressure gradient data sets, you can, build on top of that. Yeah.
Some related question, maybe it doesn't seem to, but I think it is. Is there a kind of measurement or a kind of structure that I can dream of making that would allow this learning to happen, either much quicker or in a way that would give you much better predictability than is currently done? Like, what are you missing? What are you wishing for in terms of experimental methods, experimental objects that you could get data on to make your life more interesting?
So we want to do this, right now what we do is we want to improve something. We go to whatever data we can lay our hands on, like in this case here, and then we try to improve the model, right? But ideally, you need to have a loop where you start with what you have, and then you design the next experiment to say, this is all of my model's blind spots. So get me this data if you can, and you can try to improve. That's one dimension I would like to move in. And if we have lots and lots of data, we can do more creative things with unsupervised learning and figuring out failure modes and things like that. But I really have to run because my meeting is in another building that I have to drive to. And I'm the one asking people to show up at that building, and then it's going to be 10 minutes late. But thank you very much.